So I have the honor of introducing our next speaker, who is Sarah Peluse, who's going to tell us about integer distant sets. So, Sarah.
Thanks. Everything in this talk is joint work with Rachel Greenfeld and Marina Iliopoulou. And we worked on this the last couple of years that I was a postdoc here. And we knew, well, we worked on this and then like a circle of related problems. And we knew that kind of no matter what, the determinant method would play a key role in our arguments. And while I was here, I had like multiple like really enlightening conversations with Peter about the determinant method and its history. And that was like really valuable for us. All right, so my talk is about integer distant sets. So first I'll tell you what those are. So they're exactly what they sound like. So we say that a subset of the plane is an integer distant set. R2, yeah, thank you. If the distance between any pair of points in S is an integer. So an obvious example of one of these sets is you can take just like all the integer points on the x-axis. More generally, you can take like any line, take like just a sequence of points spaced one apart on that line, or like any subset of such sets. You get an integer distant set. But it's much harder to come up with examples that aren't collinear. And in fact, it's a theorem of Anning-Erdos from 1945 that there are no infinite non-collinear integer distant sets. Okay, so they prove that any infinite integer distant set is contained in a line. And I can give you the proof of this in, I guess, like a little over one like half board. But the proof I'm going to give you is not their original proof, but another proof that Erdos came up with shortly after. All right, so we'll let S be a non-collinear integer distant set. Okay, this means that we can find 3 non-collinear points in S. So there exists some points A, B, and C in S that are not collinear. Okay, so I'll draw them. So these will be the points A, B, and C. And then we'll say the distance between A and B, we'll call it n. So n will be some integer. And then the distance between A and C, we'll call that m. Okay, also an integer. So then any other point x in S has to be an integer distance to like A, B, and C. So any x in S must lie on one of the hyperbolas in the family fancy H1, which will be all hyperbolas of the form the absolute value of the difference between the distance from x to a and from x to b will be some integer between like 0 and n. So this will be the family of hyperbolas where this equals k for all integers k between 0 and an n. Okay, note that because like s is an integer distance set, this difference must be an integer. And then we know that it can be at most n, just like by the triangle inequality. And then similarly, x must lie on one of the hyperbolas now with foci a and c instead of a and b. So we'll call this family fancy H2. Now L goes from 0 up to m. So then the key is now any element x of s must lie on the intersection of some hyperbola from the family H1 and some hyperbola from the family H2. But we've chosen A, B, and C such that all these hyperbolas are different, and so they'll intersect in at most 4 points. Okay, so we have that S is contained in all the intersections of hyperbolas from H1 and H2. And so S must have size at most 4, which is the total or the largest possible size of this intersection, times the number of hyperbolas in H1 and the number in H2. The important point being that this is finite. So that's how you prove that there are no infinite non-collinear integer distance sets. So also in this paper, Anning-Erdos showed that despite this, there are arbitrarily large non-collinear integer distance sets of like finite size. Okay. So I'll give you the simpler of their two examples. Okay, so simple example. So this is going to produce an integer distance set with like all but 1 point on a line. So we'll let's let m be some odd integer such that m squared has d divisors. Okay, so then we can find then like at least d solutions. To the equation m squared is x squared minus y squared. So let's call them like x1, y1, xd, yd, all in Z2. So then you can check, so it's easy to check, that the set m comma 0 and 0, y1 up to 0, yd, that this is an integer distance set. Okay. Yeah, so it's obvious that the distance between any pair of these is an integer, and then that the distance between this point and any one of these, that's an integer, just follows from this equation. Yeah, so this gives I'm just like exactly the wrong height. Yeah, so this gives an example with all but one point lying on a line. And Anning-Erdos also gave a family of examples with of arbitrarily large integer distance sets with all points lying on a circle. Yeah, exactly. Yeah. Right, so Anning-Erdos had two infinite families of non-collinear integer distance sets that they constructed. And so since then, like since the 40s, only a couple more families of constructions have been found. And all known constructions of integer distance sets have all but and most four of their points lying off a single line or circle. And it had long been conjectured, I guess, since at least like since back to Erdos, that kind of all integer distance sets must be of like a certain special form. So this is kind of like a vague folklore conjecture. Okay, and the special form probably has something to do with lines or circles. And the result I want to speak about today is, I guess, the first progress towards this vague folklore conjecture. So we prove a structure theorem that says that any integer distance set must have all but a very small number of points lying on a single line or circle. Okay, so we'll let S be an integer distance set contained in some n by n box. Okay, so then there exists a line or circle C such that the number of points on S that aren't on the line or circle is bounded above by like some bounded power of log n. Oh yeah, and so for people who don't know, like this is Vinogradov's notation. Like this just means like big O. Okay. All right. So using the structure theorem, we're able to make progress on a couple of classical problems about integer distance sets. Or classical questions, I guess. So this first one is usually attributed to Erdos. And so then Rachel, Marina, and I like went on that website that has like all of Erdős's papers, and we tried to find the first occurrence of him asking this question that I'll tell you. But what we found instead was him saying that this wasn't like his original question. It was a question whose origin he can't trace. So the question is, okay, so it's motivated by like all of these constructions of integer distance sets that we have involve like a bunch of points on a line and a bunch of points on a circle. So it's a question of like, what if you forbid lots of points on a line, lots of points on a circle? So it's a question of how large can an integer distance set be if it has no 3 points on a line and no 3 points on a circle. Okay. Okay. All right, so what was known about this question? So by basically quantifying this hyperbola argument I showed you and improving it in a way that like improves the implied constant, Shoimoshi was able to prove that any such set satisfies that size of S is at most linear in N. Oh, sorry. Any such set. Okay, that doesn't make sense without there being an N. So any such set S contained in an N by N box satisfies that its size is linear in N. So this was the best known upper bound, and the largest such set known has size 7. And it was found in 2008 by Kriesel and Kurtz. This was like a computer-assisted discovery. So by using our structure theorem, we can immediately improve this upper bound of Shoimoshi from linear in N to power of log in N. So if S subset of an N by N box is an integer distance set with no 3 on a line and no 4 on a circle, then okay, so then it has size at most power of log. But it could be that the true answer is size of S is bounded above by some like absolute constant. I guess if I had to bet, I would bet on that.
get on the constant?
No. Well, I have to think about it, but I think I could bet on an upper bound on the constant. Oh, yeah. Like replace this log with 1. Yeah, so then the second question we make progress on is the question of the minimum diameter of a non-collinear integer distance set of a given size. So it's a question of what is the minimum diameter of a non-collinear integer distance set of size little n. Yeah, so getting like an upper bound in this question is equivalent to constructing a large integer distance set in some box, right? And getting a good lower bound on this is the same as getting a good upper bound for the size of the largest non-collinear integer distance set in a box. So our structure theorem also applies to this question. So what was known about this? So this same paper of Shoi-Moshe gives a lower bound that's linear in n. And the best upper bound is due to Harborth, Chemnitz, and Muller in 1993. So they proved, or by constructing a certain integer distance set, they proved an upper bound on this minimum diameter of the form n to some constant times log n. Okay, yeah, so there's a large gap between the lower bound and the upper bound. Using our structure theorem, we're able to almost completely close this gap. Using our structure theorem reduces the problem of improving Shoi-Moshe's lower bound to that of bounding the size of non-collinear integer distance sets like intersected with lines and circles. So we prove that if S is an integer distance set in an n by n box, and it's not collinear, and C is a line or circle, then the size of S intersected with C is bounded above by n to some constant over log. Okay. So then it follows from the structure theorem that we get a lower bound in this question of the same shape as the upper bound. Okay, so we get a lower bound of some constant times n to some other constant. I'll go again. And we can make all the implied constants in all of our arguments explicit. So we can figure out what this constant c is. You can also easily compute what this constant c prime is, but their c prime is like larger than our c. So it's still open to determine like the exact asymptotic for this minimum diameter. So it's conjectured that the sets that attain the minimum diameter are like this example I showed you in the beginning, like sets, integer distance sets with like all but 1 point on a single line. Also still open is the famous Erdős-Ulam problem of determining whether there exists a dense rational distance set in the plane, where rational distance, means what you think it means. All right, so now I'll tell you about how we prove our structure theorem. So the rest of the talk will be sketch proof of the structure theorem. So I guess first some, I don't know, philosophy. Okay. So this hyperbola proof, so this can be viewed as an application of like low degree algebraic geometry to the study of integer distance sets. Okay, so the curves have degree 2. And there are many such applications like low degree algebraic geometry to problems in combinatorics and discrete geometry. But basically this argument of Erdős hasn't been improved. So it seems like low degree algebraic geometry isn't the way to go for integer distance sets. So our kind of new idea is to instead use intermediate degree algebraic geometry. To study the size and structure of integer distance sets. So I'll try and tell you what this means. So to start with, though, okay, so in all these results, S is just like any subset of this n by n box. In particular, we don't know that it has, for example, like these aren't like lattice points necessarily, right? They're just any points. But we can actually reduce to the case that S is contained in a lattice. And this is actually a classical argument. So for this entire sketch, actually we'll assume that S is an integer distance set contained in an n by n box. Okay, and the classical fact is that we can basically assume that it lies in a lattice. So we may assume so that S is contained in a set of points of the form x comma square root of my, where x and y are rationals, denominator divides some capital M. And okay, it's not, well, it's not super important for the sketch, but like M is just some square free. We don't know, I guess we can bound its size, but we don't need to know anything about it. And this M in the denominator has size bounded by some constant times N. All right, so to actually start the sketch, we'll let K, so K is going to be some integer parameter that goes to infinity with N. So for us, we'll take, we'll eventually take K to be like floor of some constant times log N. I'll say where that comes from later. So then, so first, if S has fewer than K elements, we're just done, because then we get a really good bound on the size of S. Okay, so then otherwise, if we're in the interesting case, we want to pick K distinct points. We'll call them like PJs in S. So they'll be of the form AJ square root of M BJ, where the A's and B's are rational. And we'll consider the affine variety, call it XK. And it'll be the set of points XY D1 to DK in C to the K plus 2, such that X minus AJ squared plus M times Y minus BJ squared equals DJ squared for all J from 1 to K. Yeah, so note that by this fact, and our choice of points PJ, and the fact that, oh yeah, I guess that's all we need. So this is defined over the rationals. Okay, so this is okay. So also now, since S is an interdistant set contained in this n by n box, the points in S correspond to certain rational points, like on the projective closure of XK. So any point X in S corresponds to a rational point in XK bar of height at most like constant times n squared. Okay. Yeah, so to understand the structure of the interdistant set S, we want to understand the structure of the rational points on this variety. Okay. I guess now I should get that down. Oh. All right, so we show that xk bar is an irreducible surface of degree 2 to the k. Right. And so it's been known, it's like since work of Heath Brown, that if you have an irreducible surface, say defined over the rationals, of like high but like fixed degree, then the rational points on that surface can be covered by a small number of low degree curves. So I guess morally, the rational points on SK bar should be contained in the union of a small number of irreducible low degree curves. Oh no. Oh well. Right, so this result of Heath Brown has been refined several times, as most notably, so refined like quantitatively by Sahlberger and by Walsh. And so we then use like a further refinement that makes explicit like the dependence, the quantitative dependence on the of all the implied constants on like the degree and the dimension of the ambient space that the surface lives in. So this result is due to Castrick. Okay. What?
Reducibility, is that easy?
Here, yeah, I mean, that's the hardest of these things, but it's pretty easy. But the irreducibility of the next thing is the hard part. Okay. So that I get the actual bound right. So for any irreducible surface V in n-dimensional projective space defined over the rationals. Yeah, okay, of degree D. There exists a homogeneous polynomial G with integer coefficients. That itself has degree. N to the 175 n squared divided by square root of D, D to the 7/2, 3 n squared divided by square root of D, then n to the square root of 3 or 2 square root of D. Oh yeah, so okay, there exists such a polynomial with the property that vanishes on all rational points of V of height at most n. But so that this isn't like a trivial statement, G does not vanish like on the whole of V. Okay, so V is irreducible. So then like if you intersect V with like the zero set of this G, you get like all of the rational points of V of height at most n being covered by some curve of this like total degree. Okay, so we apply this theorem and basically we pick K to optimize. So we pick K to like optimize this bound in terms of, yeah, so to balance these contributions. So that's where the log comes from. And so then what this gives us, after applying this theorem and projecting, is that S itself is contained in the union of a small number of irreducible low degree curves. So then the remainder of the argument is controlling the intersection of S, like with low degree curves. So it just remains to bound the size of S intersected with a curve C when C is in one of two cases. So first, when C is not a line or circle. And then the second case, when C is a line or circle, but there are lots of points off of the line or circle C. So precisely, I guess, yeah. So this condition is when the number of points not on the line or circle is like larger than like log squared. Yeah. So then now what we do is we basically like repeat this argument that we did for xk, but we have to be much more careful in like how we choose the points pj. So now we repeat and we choose points pj prime. Okay, I'll just say carefully. Yeah, so for xk, it doesn't matter how you choose them, but here they need to be chosen very carefully. And then consider the affine curve fancy C sub k. So this will be basically defined just like x sub k, but then we also require that the points aj, or like x and y, lie on like some like squished version of C. So then we also require that x square root of my lies on C. Okay. So again, any point in S intersect C, this corresponds to a rational point on the projective closure of height at most n squared. So now, so we have a similar lemma where we show that the projective closure is an irreducible curve of degree, this isn't super important, but a degree like in between two to the k and 2 to the k times the degree of C. All right. So, oh yeah, also, yeah, so these curves C, either they contain a bunch of points of S, in which case you can just deduce that the appropriate linear transformation of C is defined over the rationals, in which case like this whole curve is defined over the rationals, or the curve contains like few points of S, and so you can just get a bound for it anyway. So this this curve is also defined over the rationals. We can assume. Yeah, so we prove that's irreducible of like the correct degree, and showing that this curve is irreducible is like the entire crux of the argument. And it's different depending on whether C is not a line or circle or whether it is a line or circle. And in each case, like the choice of these points is like very important in deducing that it's irreducible. Okay, so to finish, I guess I'll just say this verbally. Yeah, so now we want to bound the size of S intersected with the curve. So now that we have like a high degree irreducible curve, we can apply refinements of the Bombieri-Pila bound to get really good upper bound for the size of this set. So I think I'll stop there.
Thank you, Sarah, for an amazing talk.
Other questions? If not all the distances are integers, but like a constant fraction of them, does some of this also work?
No, I think you really need, well, I guess, okay, you could probably do some like popularity sort of argument and get something for like a positive proportion of them, but this won't give you like a bound in the end. Like you would probably get that you can put like maybe a positive proportion of the points on a line or circle. Yeah, you should be able to get that.
Usability in those special points. So you choose many points, or you say carefully chosen.
Yeah, so So here you can pick them to be on the curve, and that's kind of easier. So you just have to avoid some like, just some algebraic condition, but then you can show like by Bezout, this is like a finite number of points you need to avoid. For this one, you need to pick the points like off the line or circle, and then you need sufficiently many of them. And you also need to avoid some like algebraic conditions. Yeah.
Can you say a little bit about how you prove reducibility?
So it is by basically, so in both this lemma and that lemma, it's basically by like some monodromy argument. You just reduce this to showing that like this as a subset of like or not this, but the like affine open as a subset of like k plus 2-dimensional projective, or sorry, affine space, just like in the normal like not Zariski topology. If you can show that that's like path connected, then you win. And so it's kind of easy to do here explicitly by just showing you have these paths and they lift. And then here you have to be more careful because, so you want to go around like certain like complex lines, but it could be, and these lines depend on the choice of the PJ primes. And it could be that they intersect. So then if you go around that, you like undo your sign change. So the choice of the PJ primes is to make sure that none of these lines intersect, and you can actually find like good paths.
So can you think of replacing integers by a ring of integers, like z square root 2?
Yes, that works. There's like, yeah, so we also know like bounds in the determinant method, like over like number fields.
Are there results on high dimensional integer distant sets?
So there are very few. So all of the like examples of sets known like are kind of come from like sets in the plane, and they're like lifted somehow. But you can put like in R4, like kind of, you can take two like orthogonal planes, and you can put like certain, if you like pick the parameters right, you can put kind of the two of these like non-collinear examples like orthogonal to each other. So we've been thinking a bit about the higher dimensional situation, and we think most of the stuff should go through except dealing with like planes basically. And like, but we don't know like what possible configurations of planes with interdistant sets on them you can have that like work, that like are compatible.
Yeah, this set of 7 points you identified on the top right board, does it have any kind of geometric structure that's nice that you've identified?
No.
More questions? Yes.
Do you think an example of replacing 7 with 8 exists?
I don't think so.
Not yet.
Yeah, well, I mean, it could be, yeah. I mean, it's been like 15 years.
Sort of like ABC and things like that, and there's a funniness problem.
Yeah, so I guess like the Erdos-Ulam problem has a negative answer if you assume ABC. Also, if you assume Lang's conjecture, and at least for Lang's conjecture, it would give you like a uniform upper bound on the size of yeah, actually I think any or uniform upper bound on the number of points like off a single line or circle. But I don't know if it attains 4.
Any more questions? Great, let's thank Sarah again.